제가 LG를 4원? 4원?
Hello and a warm welcome from my side. My name is Sebastian Schneider. I'm the Product Lifecycle Manager for Transformer and Generator Protection. Today I have the honor to present you our newest implementation about arc suppression coil control. Together with my colleague Thomas Rottenkamp, we will introduce you the new functionality in our SIPROTEC 5 platform. Thomas, warm welcome to you. Thomas is our new promoter for arc suppression coil. He is on board since March this year, and he will present the first introduction about that new functionality and some basic features of the function himself. Later on, he will show some testing capabilities of the new function. Thomas, it's your part.
Thank you very much for the introduction, Sebastian. So yeah, let us start with the webinar. So to start, let's take a short look at the agenda for today. So first, I want to give some basic information about the topic of the compensated grid and arc suppression coil control in general. Then we of course want to talk about the arc suppression coil control function in SIPROTEC 5, give an overview and look into some details there. And we also want to talk a bit about the advantages of the integrated solution for the arc suppression coil control we have in SIPROTEC 5. And then afterwards, we also want to show you a short demo of the control function. And finally, in the end, we of course will also have a Q&A session where we will answer your questions. So first, let's go a bit into the basics. So why do we use an arc suppression coil at all? Why do we use the compensated grid? So line to ground faults or one-phase faults are the most common type of faults in electrical grids. So they are quite important. And the circumstances we have in the case of such a line to ground fault depend mainly on the neutral point treatment of the grid we have. The neutral point of the grid can be isolated, or it can be solidly grounded, or it can be connected via an arc suppression coil to the ground, which then means that we have a compensated grid. And all those different constellations have their own advantages and disadvantages. But especially in the medium voltage grids, often the compensated grid is the best solution because of economical efficiency and also safety. To see a bit the advantage of the compensated grid, let's take a short look at an example. So first here we have an example for an isolated grid. We can see the neutral point of the transformer has no connection to the ground. So it's isolated. Then we have here 3 feeders, and we can see the line to ground capacities of the grid. And we also have on the feeder below, we have a one-phase to ground fault. And what now happens in the isolated grid is that we get a current circuit over all the line to ground capacities which are in parallel and then back over the fault location. And the special thing about this ground fault in the isolated grid is that the fault current depends really on the sum of all line to ground capacities in the grid. So the larger the grid gets, the larger also the fault current will get. And this also leads to a bit to the disadvantage of the isolated grid. So we can get quite high currents here if the grid is bigger. And if we now have a fault arc, then this fault arc will probably not extinguish by itself, because if the current is above the so-called self-extinguishing limit, the arc would not extinguish by itself. And we will have a continuous arc fault. And also in the isolated grid, we will normally not be able to operate the grid during a ground fault, because due to the high currents, we will also have high step and touch voltages. And now to improve these conditions, we now come to the compensated grid. We now connect the neutral point of the transformer to the ground via an arc suppression coil. which is mainly an inductance. And now we get a second current circuit over the fault location and back over the arc suppression coil. And we can see the arrows here, the blue ones, they are showing into the opposite direction now because we here have an inductive current in contrast to the capacitive current caused by the line to ground capacities. And we now can tune the value of the coil impedance to the value of the line to ground capacity, and by this we can nearly completely compensate the fault current in the case of a ground fault. And yeah, the advantage here of course is we have really low fault currents, and because of this, if we now have a transient fault arc, the arc will extinguish by itself and the fault will be cleared. And also if we have other faults like stationary faults in cable grids, we also have the possibility to operate the grid for a while in this faulty state, because we have low fault currents and we will not have dangerous step or touch voltages there. So far on the compensated grid itself and the arc suppression coil. But why do we now need a control for the arc suppression coil? The answer to this is relatively easy. It's because the capacitive earth fault current, the line to ground capacity of the grid, does not remain constant, but it changes over time. It changes due to grid extensions, but especially it changes due to switching actions we have in the grid. You also have a small example with two arc suppression coils. And for example, the arc suppression coil B is connected to a bus bar where we have one feeder with 50 ampere of capacitive earth fault current. And the coil will also be tuned to 50 ampere, so we will be compensated. But if we now have a switching action in the grid, for example, close here and open here, then this feeder will only have a capacitive earth fault current of 20 ampere. And if the coil does now remain at 50 ampere, we will be overcompensated by 30 ampere and will have a high fault current again. We will not be compensated correctly. And now to ensure that we are always compensated for the current grid state, we now need an automatic adaptation of the arc suppression coil to the current line to ground capacity of the grid. And this is where we need an automatic control function for. So why did we now implement such a arc suppression coil control function also in SIPROTEC? We have seen that ground faults are an important topic, and we really can increase the reliability of power supply by using an arc suppression coil together with a reliable control for that. And it's of course good if we can support such a function in SIPROTEC to help grid operators increase the reliability of power supply. And then the integrated solution we have in SIPROTEC comes with some also specific advantages. One big advantage is that we can significantly reduce our costs, our operating and investment costs, because we now do not need anymore a separate device for the control of the arc suppression coil. We can use the SIPROTEC device for protection and for control. We also do not need separate spare devices anymore, because we can also use SIPROTEC devices as spare devices and can use them for different purposes. We do not need separate control devices as spare devices anymore. Also, our engineering gets easier because we now only need one software, so we can also reduce the cost for engineering. And also we have a reduced amount of additional components. We have less wiring to do, and we also need less periphery components for a separate control device. Then the integrated solution also comes with a very high flexibility. We can very easily adapt the functionality we have in the SIPROTEC device. We can add new functionalities by adding function points, or we can just change the functionality which is used in one device. Especially if you're using the universal device, we have very high flexibility here, and yeah, in the planning phase until the commissioning. And yeah, we can very easily adapt this with the software. And because of this, yeah, we also can have a very much faster commissioning of our systems. And then we of course have all the different advantages of the SIPROTEC platform now. So we have now an arc suppression coil controller which has all these extensive functionalities that the SIPROTEC platform has available. So we have very flexible protocol connection. We have always the newest cybersecurity standards and features. Yeah, and have the SIPROTEC hardware also. And of course, we can combine all the other functions the platform has with the arc suppression coil control. Yeah, so far on the motivation and the general advantages of the integrated solution. Now let's look a bit into the control function itself. First, a very short look at the component we are controlling, the arc suppression coil. So here we can have different types. We can have just fixed coils. It's just an inductance which cannot be adjusted. We can have adjustable coils which are step coils, so those can be adjusted stepwise. Or we can have the continuously adjustable coils, the so-called plunger core coils, which is what we have most of the time and which is also what our control function is mainly designed for. So how does the plunger core coil work? So it has a movable plunger core which can be moved up and down by a motor, and by this we change the air gap of the coil, and by this of course we change the inductance or inductance of the coil and the inductive current the coil provides. And with the control function we can now give the higher and lower commands to the coil to control it. So, but how does the automatic tuning of the coil now work? So the goal is to always find the capacitive current of the grid, of the current grid state, and then adjust the coil to this value automatically. How do we do that in general? We do that by measuring the so-called resonance curve. The resonance curve is the correlation between the zero sequence voltage and the coil position. And we especially want to calculate the so-called resonance point, which is the maximum of the resonance curve. And at the maximum zero sequence voltage or displacement voltage, this resonance point, this is the point where the coil, the impedance of the coil and the impedance of the line to ground capacity are tuned to each other. We can also derive this equation for the resonance curve from the equivalent circuit in symmetrical components, but we do not want to get too deep into this here. And how do we now calculate the resonance curve and the resonant point? So the function moves the coil in one direction, and then the function records value pairs for the zero sequence voltage and the coil position. And after measuring some points, it will do a calculation or an estimation of the resonance curve. And after the estimation is done and the resonance curve is calculated, it will know where the resonance point is, and then the function will move the coil to the tuning position, which would be for full compensation the resonance point, but in reality we will most of the time not use the resonance point directly because the zero sequence voltage can be quite high there, but we most of the time use a slight overcompensation as shown here in the diagram. So this is how one tuning cycle works. But now we said we also want, of course, to always do a new tuning if something in the grid changes. How does this work? So how do we detect the change in the grid? So this we can see a bit here. If we have a change in the grid, in this example, we are on this grid state 1 on this tuning point. And if we now, for example, switch off a feeder, then the resonance point will be lower. And we will get this new resonance curve here. So if we now have this change in the grid, we will be on this point first, but then we will have a jump to the second resonance curve to this state 2, grid state 2. And we will recognize a jump in the zero sequence voltage. And this jump is then detected by the control function. And if the control function, it supervises the zero sequence voltage. And when it detects such a jump, it knows we had a change in the grid, and then it will start a new tuning process. So it will then measure the second resonance curve and then will tune accordingly on the new resonance curve. And all this tuning will, of course, be done in the healthy state of the grid, so that if a ground fault occurs, that the grid is already compensated. So now that we know how the control function of the arc suppression coil works in general, let's take a look at which connections we need to the SIPROTEC device. So we've seen we need to measure the resonance curve. So for this, we will need the coil position. We normally get the coil position by a potentiometer from the arc suppression coil. And to connect this potentiometer, we have a new plug-in module, the ANA ECE2EL in revision 2, which is designed for connection of such a potentiometer. And some coils do not have the potentiometer. Most of the time they have those, but if the coil has the position information in form of a milliampere signal, we would have to use another existing module plug-in module for the SIPROTEC device. And in addition to the position, to measure the resonance curve, we also need the displacement voltage, or zero sequence voltage. We can get that directly from the arc suppression coil, from the measurement winding of the arc suppression coil. So then we would parameterize that we measure it directly, or we could get it from a broken delta winding. Or in the newest version, from the newest version on, we also can get it from a free phase measurement. The function will then calculate the zero sequence voltage from the free phase measurement. In addition to the measurement, we will also need higher and lower command, of course, to the arc suppression coil, so we can give active commands to the coil to move higher or lower. So this is what we strictly need. And in addition to that, we also recommend to wire the higher and lower end switch of the coil so that the function immediately gets the information that the higher or lower end of the coil is reached. Then, of course, we can also have different signals depending on the application. For example, if we want to use the additional function for resistor control, we will see that later. We then, for example, could use this command to switch on the resistor. So far on the wiring. Now let's dive a bit deeper into the function. So here we have an overview over the arc suppression coil control function. So the main part, as we've seen already, is of course the automatic control of the coil, but we also have other parts in the function. We all have the possibility to do a manual tuning. We can switch from the automatic to the manual mode, and then we can give manual commands, directional commands, or also set value commands to the function so that the coil is moved. Then we have an automatic calibration function. This is necessary for the commissioning of the function. In the beginning, we have to calibrate the function to the coil and the potentiometer we are working with. So therefore we have this automatic calibration function, and this makes the commissioning quite easy. Together with the arc suppression coil control function, we can use different recorder and log functions. For the recorder, we can use the slow scan recorder to record a shorter period of time more in detail, or we can use the continuous recorder to record a longer time. And we have all the different logging functions available, which are in SIPROTEC, like user-defined logs or operational log. But in the future, we will also have an additional log, especially for the control functions. Then the arc suppression coil control function also has different supervision or monitoring functions included. So it will supervise whether the movement speed of the motor is plausible, whether the position of the coil is plausible, and whether the wiring of the higher lower commands are exchanged and things like that. And this of course also helps us to find when there are some wiring errors, to find the problem more easily. And we also have additional displays for resonance curve and for controller measurement. For this function, there's also really a new element for the display page. For the resonance curve, we will see the data. And also on the web UI, we have many different new display possibilities. We will also see that later in the demo. And then there will also be there is a separate additional function for control of for an additional parallel resistor to the coil. So this function is more independent from the normal coil control, but it can be used in addition. We'll also see this on a later slide. So, and since we've now reached half of the presentation, I would now forward again to Sebastian.
Thank you, Thomas, for the nice introduction about the basics of arc suppression coil control. It was really, really, really impressive. So now we start with the second part of our presentation, and I would like to show you a bit more about the functional values of the resonance curve and also what we did in our implementation for the function. So you can see here on my slides the graphic. So for the resonance curve, this is quite new for our SIPROTEC 5 system. We don't have it before. So, and I'm really proud to present these here on the presentation, on the webinar. So you can see here that the device have now the capability to draw the resonance curve, and as well, beside the HMI on the display, we have also the possibility to see the resonance curve on our web UI. So you see it here on the right side of the presentation. So this is the graph, which is actually then drawn after we estimate or we find the resonance point. So then the device or the function have the capability to draw here the graph. So, and the advantage of this makes it very flexible for the automatic control, and especially during commissioning, you have the possibility to see where is the resonance point in the grid and where's our actual target of the compensation point of the target tuning point. So, and one additional thing is here on the left-hand side of the HMI, you can see that we also spend a lot of attention here to get a lot of values to have information. What is the actual current of the coil? What is the actual resonance point? What is the detuning point? And so on and so on. That means we spend also a lot of attention to get functional values here in the display, functional values in the end, what you can send to the SCADA system. On the next slide, you see the possibility of the manual tuning here. So beside the automatic functionality, we have also the possibility for manual tuning. So that means we can give a directional tuning. So that means we can step the coil in the up direction and higher and lower, for example, or we have the possibility to reach a target position by give a certain value or send a certain value to the device, and the tuning algorithm is tuned the function to that values. So, and this is possible binary inputs where the push buttons, which is also known from the automatic voltage control. You can do a manual tuning on the HMI, or you have the possibility, and this is especially for the last point, so that means you would like to reach the target position via an APC. That means you send from the SCADA system a target position, and the coil is moving to the target position. Maybe if you want to switch on the arc suppression coil, then you would like to tune the coil to maybe 150 amps. And this is easily implemented, so you can use it for your needs as you want. So on the next slide, you see the automatic calibration. Beside the automatic tuning, we need also an automatic calibration. So, and here, additionally, I would like to point out as well here our capability of the SIPROTEC 5 platform, that you can have beside the function also a slow scan record. You can see here what the coil is doing, so what the motor drive is doing. So here we see the low position in the record, we see the high position, we see also the calibration procedure of the function. So that means we estimate the overrun, we see the speed of the motor, and in the end we see also the linear error. And of course, beside the graph on the HMI, you can see it also here in the web UI, which is additionally a good possibility during the commissioning to get the values out of the device and to show it here on the web UI. So the advantage for you, easy commissioning due to automatic calibration routine. That means you start the calibration and the device is doing everything by himself. And optional, and this is a setting in the function himself, that you have the possibility for manual linearization. That means if the linear error beside or to the potentiometer input is too big, you have also the possibility to make a linearization. So then the possibility via the slow scan record, so that means every device, every SIPROTEC 5 device have the possibility here for slow scan recorder, or to add the slow scan recorder. And we recommend to do that, because then you have a clear picture what the coil is doing, what the algorithm is doing. Afterwards, what he analyzes. This is also a good point, that you can use here each single message and also the functional values to add these to the slow scan recorder. And then afterwards, you have a fault record. You can analyze the fault record. You can send also the fault record to us, that we can do the analysis. You see the real behavior of the displacement voltage, you see the coil position, you see all the binary information here of the arc suppression coil control. And this helps you to get a clear picture of the function. This helps you as well to find the right settings. For example, if the coil is stepping too much over the day, then you get here some information out of the device, what has happened with the function and how the function is reacting on some grid changes, as Thomas was explaining before. So then we come to the easy parameterization, and here in one example in Dixie, you see the arc suppression coil is a function group as we have for protection functions, or similar to our voltage controller function. And this voltage controller, or this arc suppression coil controller, contains different function blocks. One function block for the plunger core, one function block for the coil tuning himself, and additionally, and this is optional, you can also control the resistor and supervise the resistor. Here we see the capability of the settings for the plunger core. So this means you can select the sensor, you can set the minimum and the maximum position, and you have also the possibility here on the bottom of these parameter sheet to set the manual linearization by filling out this table here. On the right side, you will see here, this is the setting sheet for the coil function, for the coil tuning. We have the function for the tuning algorithm. We have the function for the behavior in case of an earth fault, and so on and so on. So now we come to the next point, and the next point is an additional function. If you want to take the stationary ground fault, you can switch on a parallel resistor, which increase the watt-metric residual current. And so for that, the function provides these capabilities. So that means you can add this function additionally to your arc suppression coil control, and then you have the possibility to supervise the resistor, because usually the resistor is heating up during that time because you increase the current. The current is also then flowing over the resistor and heating up the resistor, and therefore you have two stages for monitor the resistor. One stage is a time-depending stage, and the another is then also a terminal stage of the function. So in a library, you can easily select what you want. You can add it to your system or to your project here, and then you can supervise the resistor. And usually the watt-metric increase of the watt-metric current is then used to detect where the fault location is, and after clearing the fault, the operation is going into the normal mode again, which is shown here on the graphic on the right side. So, as described, the stages is working independently. So that means we can have, beside the normal time stage, we can have also the terminal stage. You can activate both, or you activate only once here to supervise that the resistor is not overloaded. This gives you an additional functionality here for working or for operating with such a kind of a resistor. Here on the next slide, you will see an additional function which is now implemented with the 10.0. You have the possibility for potentiometer gap detection here, which is an additional function block which can be instantiable optionally to the function. So because over the time, the parts of the potentiometer can have corrosion, so and this causes some measurement errors, and those potentiometer gaps are detectable by these additional function block, and the missing measurements are corrected in the function himself. But if these gaps exceeded maximum length of the automatic tuning, the automatic tuning will then be blocked by the function himself and gives an alarm. So this is the function. So that means easily, like the resistor control, you can add these functions, you can set the parameter for this function, and then the function is working as you expected here. So now we come to that point where the function is available. The function is implemented with the 9.90. And now the function is available in most of the protection devices, like in a universal device, like in an overcurrent device, transformer protection devices, in the merging unit, in the bay controller, and as well also the line protection devices have the possibility to add this function. We have a very flexible configuration, so that means you can combine protection and control functions in one device. For example, you have an overcurrent device and you want to add this function additionally as a control function, so that means all functions in one box. You have the possibility as also the function to instant the function 4 times into one device, especially you have, for example, 2 coils or 2 arc suppression coil controller in one box, and you can control both independently, or you have a parallel operation. Then you can have one fixed coil and one movable or adjustable coil. The function arc suppression coil costs 250 function points, and this is then available with the version 9.90. Now, as explained, with the version 10, we implementing some additional feature like the gap detection. So When we talk about the advantages, and Thomas was also giving some hints about the advantages of our integrated arc suppression coil control, and I think one advantage for the user is that you have one device and not multiple devices anymore. So that means you can put everything into one device. It is easy to use it. It is easy to parameterize it. It is cost-efficient solution, especially in terms of commissioning and engineering. We have a powerful platform with SIPROTEC 5, easy smart connectivity regarding the communication protocols like IEC 6150 or redundance protocols available. We have the latest cybersecurity features on board, and as well the possibility from the platform to have logging functions, to have disturbance recording, and so on and so on. And this offers you really good packages to use the function on our SIPROTEC 5 platform. So, and yeah, finally, we want to talk about the roadmap and a bit of outlook. So I think you also have some questions regarding what is coming next. So we start in December last year with the 9.90. So that means the function is released with the 9.90 with the potentiometer functionality, with the ANA-ECE module and the resistor control. In February, we have the second release after the first feedback from the market. We did some improvements, especially on the algorithms for the displacement voltage. We add the user-defined display. That means you can use now the resonance curve and the calibration curve on the main display pages. You can parameterize this. With the third release, in June, we add the potentiometer gap detection, and we did some additional improvements because of the feedback from the market and of our first installations. The next release is planned in March next year. That means here we want to have an extended regulation for current injection method in symmetrical networks, which is step 1. We support here the step coil support with this release. And this is the point. Yes, we are also working on the current injection method, but the first step, we have a more easy implementation or more light implementation for step coils, and with the next releases next year, we will have also current injection method as known from the market for symmetrical networks. And we also want to offer here then a parallel control, an implemented parallel control. If you operate two arc suppression coils in one grid together, then we want to have a fixed function here, which is then easily to activate via a setting or via binary input that both coils are working together. So, and last but not least on our roadmap is also to bring a standalone, I would call it standalone device, a smart controller on the market here, which contained all the control functions beside the arc suppression coil, also the voltage controller. We want to add power quality functions to that device, and of course some basic protection functions here. This is a new device type which will come definitely on the market to have a standalone controller device available on the market here.
Okay, so now thank you, Sebastian. We will now look at two short demos for the function. So first we will have a short demo in the digital twin and the web UI, where we can see a bit the calibration process and the visualization of the resonance curve in the device and the web UI. And then we will also have another short demo where we can see a bit more about the calculation of the resonance curve and the control function, how it works. So then let's switch to my PC for the first demo. So here we have a digital twin device, which is parameterized with the arc suppression coil control function. And I also parameterized here a display page with the resonance curve. And yeah, also in the web UI, we have the possibility, for example, to go to the function values, arc suppression coil, and there we then can also see the coil tuning, the resonance curve. But for the first part, we now want to make a short demo for the calibration. So here we can go back and can go to this plunger core coil page. So here we can then see the results of the calibration. And in the digital twin, we have the possibility to do a simulation with a replay of a Comtrade file. And here we have now two Comtrade files, so one for the calibration replay. And yeah, I think I have to scroll a bit here, and then we start this file. Now we can see how the calibration works. So we do not have the measurement values yet, but we can here see the position of the potentiometer. And now we can see a bit how the calibration works. So first it will go to the lower end switch. So the position of the coil or the potentiometer will decrease. And after it has reached the lower end switch, then it will increase again. Now it will go to the higher end switch. We cannot really see the position here in the resonance curve at the moment because we do not have done the calibration yet. But now when we will reach the upper end switch, and now we can see we already got some calibration results here for the lower and higher end switch position, also the speed. And now we also get a value for the coil position. And at the end of the calibration process will move a bit in the middle area of the coil and then calculate also this overrun and this linear error. And it will probably be finished soon also. So it's still running, but now it should be finished, and we can see also the other results are now here. And after the calibration is done, if we update this again, we then will also be able to see this calibration curve here visualized. So here we can see how the coil position changed over time. So far on the calibration. Then we can also now show a very short demo in the digital twin to show the resonance curve. But therefore I just shortly have to restart. Then we can choose the other Comtrade file for replay, which will do a very short example for the auto tuning. So we have also to update or connect to the web UI again. So go to the coil tuning page here, and we can also now take a look at the display page for the resonance curve, and we will start the replay for this auto tuning function. And now we can see the coil moving. So now also the current position is shown here. It moves higher, and now we can see how the control function works. It now records some values, and now there we have a first estimation for the resonance curve. And while continuing to move, it will always update the latest result or estimation result for the resonance curve, and it will also be shown here in the web UI, but also in the display page for the resonance curve. And in this display page for the resonance curve, we also have the possibility to add some measurement values. So here, for example, I've added the resonance, the voltage and position for the resonance point, and the measurement values for position and Vn. So now the resonance point is nearly reached. So yeah, the results now should not change anymore. So we can now see also the calculation results for the resonance curve. So now we want to take a look at a second short example for a simulation. Here we now have a Siemens internal simulation which uses MATLAB and an Omicron CMC. And yeah, the Omicron CMC here simulates the behavior of the arc suppression coil and the resonance curve, and it's connected to a real physical SIPROTEC device. And here we can see a bit more of the behavior of the control function. So yeah, here we can change to my screen again, so we can show here the recording. So here, okay, on the left side, we will have some, from MATLAB, we will see the measurement values. We will see the coil position in ampere. We will see the zero sequence voltage both over time, and here below we will see the zero sequence voltage over the coil position. So this will be the resonance curve. And on the right side here we will be again in the web UI, and now here also a process for automatic tuning is started. So the model now simulates also a resonance curve, and it will the tuning will now be done. So we can see as before the coil moves, and the result for the resonance curve is updated continuously. And after ending or finalizing this estimation and calculation, it then will then position on the tuning position. So in this case, the resonance point is around 100 ampere, and the control function is parameterized with 105 ampere. So the tuning position should be around 105. And here we can see, it went a bit over the resonance point, the position, and then after measuring enough values, it went back a bit to now position onto the target tuning position of around 105 ampere. So what we can now do also with the simulation model is we can simulate a change of the grid. So we can change the resonance point of the grid here below, and in this case we will change it by 10%. So I think I clicked on 5 ampere, but 2 times, so it will be 10% lower. And we can now see this jump in the zero sequence voltage here. And now there was also a timer here. We have a delay after the jump. This was going down, and after the delay was going down, now the new tuning starts. And now the coil moves downwards first and records this values for the resonance curve. And now it already got a good estimation for the new resonance curve again. And now it will again tune to the new correct position. Now the resonance point is around 90 ampere, and 5 ampere overcompensation is parameterized, so it will go to 95 ampere. And here in the web UI we can also see all the other calculated values like the wattmetric residual current, the relative damping of the grid, and such things. So now we were also able to see this change of the grid and how the new tuning process was started. In the web UI, of course, we also have other possibilities. We, for example, can take a look into the logs. So we can open the operational log. Here we can then see what happened. It was not tuned. The commands were given. The motor moved. Then it was tuned. And we can, for example, also look directly into the recordings which were done. Here we can also we take a look in the, as an example, into a slow scan log. yeah, we can also directly visualize this in the web UI. And yeah, in this case, yeah, we have recorded the coil position in different ways and the 0 sequence voltage here. And yeah, but we can also record calculated values like the wattmetric residual current, which was calculated over time. And if you go down, yeah, we will also see the binary signals here, depending on what we routed. And in this case, we use the starting of an auto-tuning process as the trigger for the record. So yeah, if we do it like this, we can, with this low scan, always record when a new tuning is started. And of course, we can also download the recorders from the web UI here. Yeah, so these were 2 short demos. I hope it helped you a bit to get a bit of an impression how the control function works and what possibilities we have here with digital twin and web UI, and also with the very flexible parameterization for recording, etc. So this would it be from my side for the webinar. So at this point, yeah, we have finished the general part of the webinar. We now have time for your questions. Please ask your questions and we will answer them in the Q&A session. And I will then forward again to Sebastian for the Q&A session.
Hello, and again, a warm welcome from my side. You will already see that today I have the honor to answer all the questions. Beside me is Sophia. Sophia is new in our team. Thomas is not available today for the questions. And Sophia will raise all your questions to me, and I try to answer the questions. Sophia.
Hello, also from my side. So let's start with the first question from the audience coming from BF. Current injection is often required in very symmetrical grids. When will this be available? How can a grid customer know if current injection is needed? That is, how big must the residual voltage in the neutral point be for the coil to function properly?
Okay, good question. Yeah, I will answer the question in 2 parts. Definitely, we are still working on the current injection method. You have seen that on our roadmap. So with version 11, we bring or we release the step coil first with a, I would call it, passive current injection method. And with version 12, we start, or after version 11, we start to implement also the current injection with multiple frequencies, and this will be available then with version 12. And yeah, the second part of the question was related to the residual voltage. Luckily, our SIPROTEC 5 platform is very advanced in terms of the measurement. So that means we have a high resolution and we have a very good accuracy. And beside that, also our algorithm is able to measure very low voltages. Usually this residual voltage is below 15 volts, otherwise you have transient over voltages, and the lower limit is below, I would say, around 0.5 or a bit lower. It depends a little bit on the disturbance and the displacement voltage. If we have high harmonics or if we have some other disturbance there, then of course we need to keep a small safety margin to detect these displacement voltage properly. Next question, please.
Okay, thanks for clarifying that. Let's move on to the next question from IW. The CDC type BAC used for regulating the coil up and down is a CDC type that is not supported in the SICAM 8 family. Do you have a recommended workaround for this?
A recommended workaround, yeah, it's a good question, because that's the truth. So BAC is not supported yet in the SICAM 8. This requirement is raised to the colleagues from the SICAM platform. and a workaround needs to be worked out by us. So I will come back with the workaround when we answer the question afterwards. So then I will definitely write some sentence regarding a workaround, how we support these BAC DDC type.
Okay. Next up, we have a question from CG concerning the resonance curve. How is tuning performed? How is the resonance curve calculated? And what grid parameters will be required?
Okay, the tuning is performed in the first step by moving the coil. So that means we tune the coil and we check the displacement voltage. So we have different tuning strategies for it. So that means we just looking if the displacement voltage is increasing and decreasing around the resonance point, or we have the possibility by the strategy to move the coil over the whole range. That means from the low end to the high end, and then we calculate the resonance point then, because the highest expected displacement voltage is always the point where we have the resonance point in the grid. Or and this is the last strategy for the regulator. We can avoid the resonance point, because at the resonance point we have the highest transient voltage in the grid, and this can lead to any damaging. So therefore, we have these kind of different control algorithms at the moment. And these parameter, what we need is just we measure just the displacement voltage for our controller.
Okay, thank you for the explanation. Let's take another question from the audience, this time from MB. Do Siemens devices support current injection or multi-frequency current injection methods to determine resonance curve? And how do Siemens arc suppression coil regulators detect the resonance curve?
Okay, as I said before, and the last question, so we definitely support the current injection method, because this is, I think, state of the art. There is also the idea to implement an algorithm which is working without the current injection method, to avoid that we need further equipment. So and we can also the idea is that we then also work with very low displacement voltage, of course, for the most of the customer, and current injection method is well known. So, and that's why we also step into that controlling with current injection method, also with multi-frequency approach. And then, of course, depending on the application, we can inject the current injection, or we inject the current via the auxiliary connection or winding of the arc suppression coil, and use that for determine or for calculating the resonance curve.
Great, thank you for the answer. Here's another question coming from the chat. IW wants to know, what are the pros and cons by tuning the regulator as slightly overcompensated versus slightly undercompensated?
Oh wow, that's a deep technical question. Usually, as I heard, our grids are mostly overcompensated. Because overcompensated have the advantage that we can extinguish the arc on the fault location. So there is no rest capacitive current anymore, just a wattmetric current, and we have a slightly higher inductive current. And cons for the overcompensation is that we have the risk for resonance, risk for resonance between the coil and the network capacity. We can have transient overvoltages, and sometimes the protection may operate wrong when it is when we have slightly inductive current. Undercompensated is also possible, clear. But for undercompensation, we have a rest of the capacitive current, and the self-extinguish on the fault location is not given, is not probably work. So that means we have the risk that the arc is not extinguished. But for the fault location detection, we have a stable earth fault detection for the watt metric relays, because the phase angle between the watt metric current and the capacitive current, it's more clear. So but the practice shows that we always working, or most of the grid operator is working slightly overcompensated. And I think this is as well a philosophy of the different operators. Yeah.
Okay, we have another question. OR is asking, what level of healthy state residual voltage is required by the controller?
It depends. As I said already before, it depends that the voltage is easily detected by the algorithm. So that means we have a kind of safety margin between the residual voltage and the disturbance voltage, what we usually have in the grid. And we're currently doing some investigations and measurements and tests so far, that we also try to figure out what could be the lowest displacement voltage for our implementation, so that we can give a recommendation to say, okay, this is the lowest level. Usually the level is 0.5, could be also lower. It depends a bit on the disturbance, which is usually caused by transients or caused by harmonics and so on. So, but finally, I'm the opinion that our implementation is working quite well, because we had a lot of experience regarding filters and filter algorithms and so on, and we improved the functions with the latest version again. That our function is working very stable in terms of any disturbance and low voltages. So, that's the answer what I can give to that. Yeah.
Okay, thanks for clarifying that. The next question is also from OR. Maybe you could give some insight into this. How is the parallel operation of two controllers managed?
That's a good question. Yeah, of course. Usually you can have two arc suppression coils in the grid. Both are working independently when the grid is disconnected from each other or separated from each other. If both grids are connected to each other, so then of course one of the coil is fixed and the other coil is then operating or moving in that regard and do the compensation. So, and in that regard, of course, we are also working on a parallel option. So currently you can do it with a small CFC plan. That means you can check the position of the breaker. So if both grids are connected together, then you can set one of the coil to a specific set point value. You say, okay, the fixed coil have a value of, for example, 300 amps compensated inductive currents, and the other coil is doing the operation. So if it is necessary then to move also the fixed coil, no, don't worry. So you can do that as well. So you give directly a manual command to the fixed coil and increase or decrease the value, and the rest, the flexible coil is doing it, as usual. So, and this is possible at the moment with a small CFC plan, like a small application node. But later on, we will have an integrated function for that.
Okay, thank you. Next up is a question from IW. Is there another way to start the calibration except routing the start calibration via a binary input or a function button, for example, via LHMI, or going online in the IED via web browser?
That's also a good question, and I think this is also an improvement, and I think in version 11 that we have the possibility to control also the control, the arc suppression controller via web UI. So that means we can start the calibration, we can start as well. Also, we can switch from manual to automatic mode. This shall be possible with version 11 via the web browser, the web UI, or directly on the HMI on the device. Yeah. And of course, sorry, it is always possible via protocol to start the calibration or to start or to switch over from manual to automatic mode, of course.
Okay, thanks for clarifying that. Then we received a question from BF. From your experience, what are the practical advantages and disadvantages of using a direct potentiometer input like NIE-CE revision 2 compared to a 4 to 20 milliamp transducer like NIE-CA?
It seems that BF had a lot of questions. Yeah, that's good. My experience. Okay. Definitely, most of the coils have a potentiometer installed, but of course there is no difference between. I would say, that's my gut feeling. I would say 80% of the coils have a potentiometer, and the rest have sometimes 4 to 20 milliamps. I think there is no advantage or disadvantage. I think one of the points is that these potentiometer inputs usually have not the input, the potentiometer have a weak point, because over the years you get corrosion on the potentiometer and the coil is usually not operating over the whole range. So that means we can have this kind of gap. Therefore, we have the gap detection. But anyway, you can use the potentiometer input via the revision 2 NIE-CE module, or you can also use the 4 till 20 milliamps transducer. Therefore, you can use the NIE-CA module. You can also use, for example, the IO218, for example, where we have also fast transducer. IO210 has also fast transducer. So I think there is no disadvantage in terms of the application. It depends a little bit on the coil, and it depends what is available, but of course we have the full flexibility. And now with version 11 we bring as well the step coil, and for the step coil it was necessary that we are implementing also the calibration for the 4 to 20 milliamp transducer. So that means now we have a calibration functionality also for the 4 to 20 milliamp transducer here available in our platform. So which is also very interesting for the voltage regulator.
Okay, very interesting. Thank you for the insight. Next up, we have another question from BF. After successful calibration, how do you normally perform the manual linearization? The manual says to move the coil step by step, read the mechanical current value, and enter the corresponding percent value in the SIPROTEC table. Do you do this continuously while stepping the coil, or is it acceptable to write down all the mechanical values first and then enter the entire table into SIPROTEC afterwards?
Yeah. You can do it just online by reading all the different steps. That means you have usually you have this kind of control or a manual control panel on the coil, where you see the position and the corresponding inductive current, and you can move the coil manually, and then you can read the corresponding value for the potentiometer input. And then you can put all the values in a table. I think up to 20 pairs of values you can put into the table, and afterwards you download the new parameter set with the corrected table. That means with the manual linearization to the device, and then the device is using this manual linearization. I was doing it once during a commissioning, and I was very surprised how accuracy then afterwards are the values on the HMI and also the values on in the fault record are.
Okay, thank you. The next question is from ERZ. How does the adaptive control of the arc suppression coil improve the reliability of power supply in networks with high penetration of underground cables?
Okay, how does that? Yeah, okay. The advantage the advantage especially of compensated networks is that that we can that we can fully compensate the capacitive current, especially when we have distribution grids with very long cables and with a lot of cables. Then we're increasing the capacitive current in the network, and we can compensate the cables or the capacitive earth currents with the inductive. So and due to the fact that these underground cables have sometimes sorry due to the fact that these underground cables can have a short circuit, phase to ground failure, we can compensate these phase to ground failure. Wattmetric current is left, so it depends how high is the wattmetric current in the network. But finally, due to the compensation, we can operate the grid, and we can easily, and then afterwards, of course, we can easily detect where the fault location is, and we can isolate the fault location. And this offers a high reliability and availability of the power supply in such a networks. Yeah.
Okay, thank you. The next question from the audience is coming from UV. Can ASC be oil immersed, or is dry type construction also possible?
Ooh, good question. Yeah, dry type, I think for the movable coils, I've never seen dry types. For step coils, I think there are dry types available. So, but I'm not the expert for arc suppression coil. So therefore, maybe I need to investigate a bit, and I will write down afterwards my answer to that one.
Okay, the next question is from BC. Is the controller compatible with ASC manufactured by Siemens, or is it more universal?
This is universal. So Siemens, I know that Siemens is also a manufacturer, or Siemens Energy is manufactured arc suppression coils, but it's also it's also universal to trench, or universal to other manufacturer like EGE, for example. So there's, because the idea and the physics behind is the same. So therefore, there is no difference regarding the arc suppression coils. Yeah.
Okay, so the next and at the moment also the last question in the chat is coming from BD. For the plunger coil, is there any limit switches provided to independently cut out the motor when the plunger reaches the extreme positions? Because there could be a possibility of failure of the command contacts of the SIPROTEC relay, right?
Yeah, we supervised as I think it was presented by Thomas. Of course, we are using the end switches, and if the motor, so that means this question is going related to overrun of the motor. And of course, if we are reach the end position, then we trigger the motor switch. So that means there's no risk for an overrun for the motor anymore. And we also supervise, and this was shown by Thomas as well. We also supervise the moving of the motor and so on. So that means there's supervision function implemented in our function. So, and this is supervising the end position. This is also supervising the motor speed, of course. That means we give a signal when something is going wrong, and in the end, if something is going wrong, then we can also proceed the trip for the motor trigger. So these are the last questions so far?
As far as I can see, we have answered all the questions from the chat.
Okay, Sophia, yeah. Thank you very much from my side, or from our side. Thank you, Sophia, to be here. And we will answer all the questions afterwards. You can download then, you get an email, I think, and you can download all the questions with the respective or related answers from us. And thank you very much that you are joining our webinar. And I'm very happy to say hello again when you're joining the next webinar with us. Thank you very much. Have a nice day.